In this video, we'll be looking at the steps for solving radical equations. Remember, when we're discussing radicals, we're talking about things like a square root, a cube root, a fourth root, and we want to be able to solve for a variable in this type of equation. I've listed here the steps for you, and we're going to do a couple of examples. The first thing you need to do is isolate the radical. You then need to raise both sides to the correct index power. You will repeat these steps until all the radicals are eliminated and then solve for the variable. It's vitally important in these that you check for solutions, because when we square both sides, that can create problems if there's a negative answer, and we know that we cannot take an even root of a negative number without getting an imaginary number. Let's begin with an example where we have something like the square root of 1 minus x minus 1 equals x. Step 1 tells us to isolate the radical, so we need to isolate this term. To do that, I'm going to add 1 to both sides, which leaves me with the square root of 1 minus x is equal to x plus 1. Our index in this case is an understood 2. I'm going to therefore raise both sides to the second power. Raising a square root to a second power eliminates the radical, leaving me with 1 minus x on this side. And over here, remember that 2 is not distributed. Rather, it means that the entire expression is squared and we will need to FOIL. This leaves us with 1 minus x equals x squared plus 2x plus 1. And then getting all of our terms on one side, we end up with x squared plus 3x equals 0. Notice the ones cancel. First thing we do when we're factoring is we always look for a greatest common factor. In this case, it's x, which leaves us with x plus 3. And the zero product property tells us that when two things are multiplied together, one or both of them must be equal to 0, which gives us two solutions of x equals 0 or x equals -3. Again, make sure that you check your solutions to confirm that nothing happened in terms of negative numbers. So we go back to our original equation. I'm going to plug in 0 first to make sure that it works. 1 minus 0 is 1. The square root of 1 is 1. So I end up with 1 minus 1 equals 0, which is a true statement. Now using -3, I'm going to plug in the square root of 1 minus -3 minus 1 equals 0. This becomes plus a positive, so I get the square root of 4 minus 1 equals 0, or 2 minus 1 equals 0. 2 minus 1 is 1, which does not equal 0, so this solution does not work. As a second example, let's look at a situation where we have two radicals. Consider the square root of x plus 1 plus the square root of x plus 2 equal to 1. According to our steps here, we need to isolate the radical. Since there are two radicals, we're just going to isolate one of them. I'm going to subtract this entire term, which leaves me with the square root of x plus 1 is equal to 1 minus the square root of x plus 2. When I square both sides, again, raising it to the index power, which is an understood 2, on the left side, the radical disappears, but on the right side, I once again have to FOIL. Do not distribute that squared term. When I, again, do this side, the radical disappears, but over here, when I do my first terms, I get 1 times 1, which is 1. Here I get minus the square root of x plus 2 minus the square root of x plus 2, which gives me minus 2 square root of x plus 2's. And then my last terms, when I multiply those together, I'm going to get a positive, and a square root times a square root makes the square root disappear. Remember that our third step here was to repeat steps 1 and 2 until all the radicals were eliminated. So I need to isolate this radical. These x's cancel, these 1's cancel. So I'm left with 0 equals -2 square root of x plus 2 plus 2. I'll subtract 2 from both sides, leaving me with -2 equals -2 square roots of x plus 2. Again, trying to isolate the radical, I'll divide both sides by -2. And so I get 1 is equal to the square root of x plus 2. Now to get rid of that radical, I raise it to the index power, which again is going to be squared, which leaves me with 1 equals x plus 2. Subtracting 2 from both sides, I get x equals -1. I am again going to check that solution. So I go back to my original problem and I'm going to plug in -1 plus 1 plus the square root of -1 plus 2. And I want to see if that equals 1. This results in 0. This results in the square root of 1. And the square root of 1 is 1. So the solution works. Last but not least, let's look at one where it's not a square root. Consider something such as the fourth root of x squared plus 8x plus 7 minus 2 equals 0. Follow the same steps by isolating the radical. I'll add 2 to both sides, which leaves me with the fourth root of x squared plus 8x plus 7 equals 2. This time, instead of raising it to the second power, our index here is the fourth power. So I'm going to raise both sides to the fourth power, which results in x squared plus 8x plus 7 equals 2 to the fourth power is 16. I now have a quadratic. I have 3 methods for solving quadratics. Again, they are factoring, taking the square root, or using the quadratic formula. I'm going to factor, so I need to get this equal to 0, which results in x squared plus 8x minus 9 equals 0. Using our AC method, this factors into x plus 9, x minus 1. And our zero product property tells us then that 1 or both of these must equal to 0. So x is either -9 or x is 1, but I have to check those two solutions. When I check -9, I get -9 squared plus 8 times -9 plus 7 minus 2, and I want to see if that equals 0. The fourth root, -9 squared is 81, then minus 72 plus 7 minus 2 equals 0. 81 minus 72 plus 7, we're going to end up with the fourth root of 16 minus 2, and the fourth root of 16 is 2, so 2 minus 2 is 0. Checking 1, we have 1 squared plus 8 times 1 plus 7 minus 2. Again, that gives us 1 plus 8 plus 7, resulting in the fourth root again of 16 minus 2, which is 2 minus 2, which equals 0. And both solutions work.